Sharks, we're the team behind BeeBot, the world's first bee that hates flowers.
While traditional bees waste time collecting pollen, that doesn't sit well with us.
Instead, our BeeBot does the opposite. It avoids flowers effectively, intelligently, and passionately.
And today, we're seeking for a modest investment of $1 million in exchange for 0.5% of our company.
We will now be doing a short demonstration.
One eternity later.
I don't think your product is gonna do well. For that reason, I'm out.
While a bee is hate the flower, I will be out.
Because of their reason, I'm out.
Thank you, Sharks. Our solution was amazing. What went wrong?
I think our product just needs a bit more fine-tuning.
Yeah, I think we need more team members.
So for Android, we split it into two screens, Bluetooth and tasks. The shared state is managed in an overarching main activity instance, including Bluetooth service. Bluetooth service manages all Bluetooth functionality like permissions and connections. Bluetooth message is an API or schema to our RPI, and the rest are view models and fragments for our UI. For UI, we have a toggle button to switch continuous scanning on and off, device cards from available devices, a message log, and disconnect button.
On our map, the BeeBot can move freely among flower obstacles which users can drag from its own grass patch. Add robot places the BeeBot, reset clears the map instantly, send position transmits obstacle data, while task 1 task 2 sends commands to the RPI. The drive button opens up the slider for precise direction and speed control for BeeBot's real movement. Our design is built around usability and visual clarity, featuring a clean pastel theme where each section, map obstacles and controls, is clearly separated for a clutter-free layout. Overall, we emphasize ease of use with a creative nature-inspired aesthetic that stands out from typical interfaces.
Raspberry Pi is a communication center connecting Android, laptop, and SDM. We created a protocol to ensure efficient communication between each parts, and we also consider the multi-threading issue. We run 3 parallel threads, a Bluetooth thread listening to Android pad, a WebSocket thread talking to the PC for Algo and CV, and the SDM manager thread driving the motors. This thread passes data through thread-safe queues, so messages never block each other, commenting results out continuously. On the CV side, we capture over 1,500 images with the RPI camera across lining and angles. When annotated with polygons via RoboFlow and use augmentation to harden a dataset such as brightness, blur, and noise. We also train a YOLO-based model, which is 0.99 accuracy. At runtime, the RPI streams video. When a recognition commands arrive, we grab a frame from the stream, apply immediate or Gaussian filtering to end detect. For the second task, we track the latest direction continuously and immediately feed it to SDM, so the robot reacts faster with no stalls.
Our project, the BeeBot algorithm, is a two-layer system for smart robot navigation. It combines path ordering and motion planning, turning a map input into optimized movement commands. The first layer tests different obstacle orders using Hamiltonian logic to find the shortest or best possible route. The second layer uses a modified A-star with turn penalties and collision checks for smooth and safe motion.
Once the full path was planned, we optimized the robot's movement. The algorithm now merges straight segments into single commands, reducing delay and motion jitter. Our algorithm tests multiple routes and picks the one with the shortest distance and least turns, as seen from the path turn cost set in this code. The robot was also recalibrated to take a precise 29 by 29 cm turning radius, perfectly matching the 90-degree turns planned by the system. In the end, BeeBot was designed to achieve fast, smooth, and accurate navigation, fully aligned with our simulation.
In order to improve real-time performance, we implemented various features. To compensate for the gyro's inherent drift, the magnetometer was configured to offer long-term stability. A custom calibration routine was developed to offset hard and soft ion distortions. This led to an accurate 90-degree turns for a task.
Free auto task scheduling adds overhead and delays, limiting fast control performance. The CPU wastes time managing timing and data, causing jitters and less accurate results. Through DMA, sensor data transfers directly to memory, and timers generate precise signals, allowing the CPU to focus on control logic for faster, more reliable performance.
Moreover, by implementing a circular DMA buffer, peripherals such as the UART connected to RPI can transfer data directly without requiring CPU intervention. This offered smoother and uninterrupted flow of data for both task 1 and 2, while ensuring sensor accuracy.
Unfortunately, our task 2 went off path during the return journey due to a heading correction issue leading to a disqualification. It was tough considering the time and energy we put into the project. But through it all, we learned so much about resilience, teamwork, and each other. In the end, it wasn't just about building a robot, but building growth, friendship, and pride in what we achieved together. Thanks for watching.